Okay, so let's continue from where we stopped. Okay, I think we have discussed this. Yes, we have discussed this. So let me go to another very nice example that I like, that allow us to put in practice what we have discussed before about how to use Python and CUDA. So this is in the next set of examples. It should be 8. Okay, so this I think you are all familiar with the idea of fractals. So this is so fractals is you know, this picture that you zoom in and zoom in and zoom in, and it's never end. It has same patterns as you zoom and zoom. So here we can use what is called Mandelbrot set, which is a subset of the fractals big set, and it's based on the idea that we have complex numbers, and if we have a function, let's say that we have a function f of z, and this is z is a complex number, and then we're saying that we take this complex number, the square plus some a constant, and this is bounded and will not diverge in the sense we applied it again and again, and this will not diverge. And this f of z, we fit it for the next iteration as the value of z. But let me go to the algorithm. This you can find it already online in Wikipedia, for example. And the idea is what I have tried to discuss. So let's say that we want to make a picture like this one, this beautiful one, and we restrict it in the range between -2 and 1. This is the range of x, and between -1 and 1 for y. Okay, and there we need to do every pixel here. You can specify as many pixels as you want. But for example, if we are working on one pixel, we can do a while loop where this application of the function, it does it up to 1,000 times. Okay, so you start with a complex number given of the first coordinates that are defined. So you have x as the real part and y as the imaginary part. These two steps is to do the complex multiplication that is applied here, plus c, which is, for instance, the x0, y0, and then you iterate. Okay, as long as this does not exceed 4, this is the algorithm, and then when it stops at some kind of iteration, we can choose color based on this index. So this is the algorithm. It doesn't matter now all the details how this has been developed. Now, just for the sake of practice, we want to try to put such an algorithm on a GPU. And I have prepared the code because it will take some time for someone to implement, so we can go through and see how we can apply what we have learned for this kind of example. Okay, so yeah. So let me go through step by steps with the presentations so we don't miss anything. So one step to do it is to do the standard for loops with Python. So you go through all the pixels in that page, and you call this function that this Mandel function. And yeah, it should be very slow because we know that for loops in Python are very slow. So this will be the one way that we will do it. Now, the other way is called NumPy, and this is this provides this library that you can install with pip install NumPy. It provides just-in-time compilers. So you know that Python is a scripted languages, and if you want to do some for loops, it's very slow. However, if you compile that piece of code to a low-level machine code, this is expected to give significant improvement. And this is what NumPy can do for us, to provide us this just-in-time compilers. And the more advanced approach that I will follow is to use NumPy, but it has also the CUDA approach, in the sense that it will compile something which will be in a CUDA kernel, and the hope is that this will be much faster before all the previous cases that I have mentioned. But you need to rewrite a few pieces of code. You cannot directly do it as in the second case and work. As we already described, you need to think about the CUDA blocks, the CUDA threads, access of data, and this is what one needs to be careful with the third approach. Okay, now, yeah, let's see this example because this is the most crucial part. Okay, let's see the function. This is the standard function that we'll need, which takes coordinates x and y on this figure. So let's say the location for each pixel. And then from that, it creates the complex number we mentioned, C. And then it repeatedly applies the function that we mentioned. It makes them square. So Python needs how to do complex multiplication and addition of complex. However, if the absolute of z is the absolute square of z it's greater than 4, as we said, we stop. So we get this maximum number of iterations that we did in order to map it to a color. Okay, so this is the function that does all the trick. However, in order to be able to complete the whole fractal in this code, we need to go through all the pixels. I mean, the function here just does one pixel. So we need to know the width of our picture. This is what it does here. It takes the mean and max, as I said before, -2 and 1, -1 and 1, for example. And it finds the pixel size. And then given, and it does a for loop over all the pixels. And it has these two pieces, the x and y, or real and imaginary, that I put here. And then it gets the color. Okay, now the inters, you can play with it, how many max inters you want to put here, but the picture should not change much. And yeah, the color that we get, we put it in an array, so we can map it to some colors that we can visualize. Okay, so let's go to the first of the cases that I have in the presentation. So we create an array. So a picture is just an array of colors. And I'm just making it to be 1024, 1533. This you can change. Okay, and this is will change you the resolution in your picture. And then just some timing. You start the timer, you create your fractal, and then you compute the difference, and you can save the picture. So for instance, here I use from pile up the image save just to save the images. Okay, and this is the first part. And here, yeah, here I multiply by 100 because this piece was very slow, so I make it. I make the resolution here smaller, and I make it 100. So in the rest case, I have one more zero here and one more zero here because they would be much faster. The other case, however, because this is slow, I make it smaller the array, and I say here, okay, I make it 2 orders of magnitude bigger to be able to compare. Because in the other case, as you will see here, I have one more zero here because they will finish faster. Okay, let's go to the other two cases that we say from NumPy, we will get this just-in-time compiler, and I will also use the peerage that will allow me behind the scenes to use parallelization of the for loops, like you do, for instance, with OpenMP that you break for loops. Okay, and the way that now this works is that you decorate your function, your Python that you function that you wrote, like this one. Okay, and yeah, this is the same as what has been implemented above, in just that I jitified it. This is what we say. And now, in this case that I create the fractal, I'm saying that here I want to use the parallel approach. So behind the scenes, you will do it in an OpenMP way. And here in the for loop that goes over all the pixels in the x-axis, I use a parallel range. So this should be able to handle this NGT, in the sense that here there is a parallel for loops. So remember, this just compiling a O level, like you will do in C, and this will be able to handle parallel loops. Okay, now we make an image here that has 10 times more pixel here and 10 times more pixel here, so 100 more. And I create the fractal as above, and here you can see that I do it twice. I do it one before start the time. And the reason I'm doing that is that when the just-in-time compiler kicks in, it will take time to compile, okay? And I don't want this compilation time to pollute my timings. And because this just-in-time, it will happen just the first time, okay, you need to call it once at the beginning, so you have somewhere cached the compiled files, and then the next time you rewrite is the real time of how much time it takes to run. Okay, so the next step is that I put it between my timers, and I create the image. Now, again, 100 times more expensive than the first case I mentioned. And okay, one can write also the image if you want to see the image. And the first and more interesting one is that is to put it on CUDA. Okay, now NumPy, as I said, has also the CUDA and just-in-time compilers. And here, this mandel is a function that I have specified above. So what it does here, it says, take this mandel function, okay, and understanding that this is a device function, like as we did before, we see that we say we put the keyword device if it is a function that will be called from the device and execute of the device. And we say to CUDA and JIT to compile it for us. So this step will compile the device function. Now, one step closer now, we need to have also the kernel. So what we can call from the host and execute on the device. So this is where we need to do some modifications. So here we need, of course, the width, the height of the image. We get the pixel size as we did before. However, the different thing that we need to do now is to remember that we have a grid in CUDA. And here I'm saying that I need a two-dimensional grid. Okay, and in this two-dimensional grid that I create from these sizes, I need offsets because different blocks will work on different locations of this image. Okay, so my grid X, let's say it's multiplication of where is my block and where is the thread I'm executing. So I need them here to find my upper limits. Okay, so this is actually a step inside this block. So in each block, it has to do a piece each thread. So this jumps the block. I have to put a cartoon so it will be more easy to understand, but I don't have it right now. And it actually starts from this one point each thread, and then it jumps. And this is done with a step grid.x, and it goes up to the width. And different one will start with a different start x and start y, based on the location you are on the grid. Okay, and then you need to find the correct location, not the local one. Those are the local, the x that you have here are the local ones. And then you map them to the full ones, given the shifts that we specified here. And then here is you call the Mantle GPU. So the one that we compile here, the device function, we give it to the kernel. Okay, and this will call it again and again in every for loop that it does. But of course, here we will create a lot of threads and blocks. I will show here. So this is the block dim. Block dim means, as you remember, how many threads we want per block. And here we do it two-dimensional. It's easier when you have two-dimensional images to use two-dimensional blocks. And we made also our grid of blocks two-dimensional. This you can play with them, and then you need to put this in the device. This Gimage now is on host. You put it in the device. Okay, so you get a pointer the image, and this is the one that you need to provide to the kernel. Okay, and of course, as we did with the CPU code, you need to provide how many blocks you need and how many threads per block. Okay, so this is now a tuple with two dimensions. And then when it's finished, this image is on the device, you copy it back to host. Okay, now it's again the same story. I put my timers. So here I forgot to mention that I do it once just to compile, okay, as I did it in the previous case, because especially the compilation for the NVCC, it's very, very slow. And yeah, here I do it in time, and that's it. This is the code that we need. So do we have questions before I try to run it? Okay, no questions. I hope that you have understood the basic idea, at least, of being able to do just-in-time compilation also in CUDA. Okay, let's do Python and then run the script. Again, make sure that you are on a GPU node. Okay, so let's see if we understand what this tells us. We say the first case is the standard Python way with the very slow for loops of Python. So in that case, it takes about 400 seconds, which is not what it took, obviously. It took 4 seconds, and because I multiplied by 100. So as I said, I did this just for the sake of comparison to be fast enough so we can see the timings. Now, the second one was just in time compilation with a standard C code, and you can see how much this improves the performance. So for loops in Python tell us it's very, very slow, so be careful. Now, we go to the third case, which is what we put on the GPU with just those simple modifications that I discussed. And you can see compared to the CPU code, by the way, this CPU code is not just one core. It will use all the cores available on the node. And because I have put this P range, as far as we remember that we will use OpenMP behind the scenes. But yeah, even with that, you can see that we have a bit more than order of magnitude improvement when we use the GPU. Okay. Now, if there are no more questions, yeah, I forgot to mention that this will create 3 images about the fractal. If you try to download them, it will be an image like this one. Okay, in case you want to play with it and see it. Now, I want to proceed to discuss the last point of the training. I want to know how many of you are familiar with distributed computing. First of all, do you know what is distributed computing? What can tell me?
You mean like on a cluster, or like on a slurp?
Yes,
cluster?
yes, I mean on a cluster.
Yeah, okay. Yeah, I am. Yes.
Okay, good. But I will try to briefly explain it. So if you have a problem which is parallelizable, and you have a lot of computer power, a lot of nodes like the Cyclone, you can distribute this the workload of this problem to different processes. For instance, you can give a piece of your data on one node, a piece on another, and a piece on another. Of course, then distributed computing needs the memory to be different for each process. This is different from the shared computing in the sense that share, it's the memory, it's visible and shared between the process. Here it is not. If we want to exchange information, we need to find ways to do it. Okay, so in the distributed computer, like what we see now on Cyclo, we have a front end that is mostly doing the coordination. So you can compile your code, for example, and you may do some archive and this kind of things. And this head node, this front end, through switches, Ethernet switches, it connect to the compute nodes. And usually the compute nodes are not connected to the Ethernet, usually for security reasons. Okay, and yeah, if you have many of those nodes, this is what makes a supercomputer super. Okay, and for example, on Summit, that I mentioned before, you have, instead of these 3-4 nodes that you see here, you have more, 4,000 plus. But the way that you design the Ethernet communication between the nodes can be very tricky, and it can affect the performance. But okay, beyond that is introductory things about what is distributed computing. It's important to understand what kind of libraries we can use to use distributed computing. And the most standard approach that I know is using what is called message passing interface. So in this interface, it allows us to pass messages from one of the process to another. Okay, you can do also a broadcast from one process to all of them. You can gather from many processes to one. So it provides us all this kind of functionality. And this has been implemented in C++, but of course, Python has an interface to that, and we will use it later. So the idea is that when we have an application which is capable of using the MPI, so all the processes that we create execute the same piece of the code. But if we want to handle differently the process in terms of how they will access data, they can access different locations of data. They need to have a different ID, different identity, and different rank, call it whatever you want, in order to be able to identify our process, as we did, for example, with our thread index. Okay, now we will do it as an index for our MPI process. Okay, and of course, with if conditions based on the ID, we can do different things. But since now we're talking about a parallel way of doing the processing, the idea of synchronizing it enters also, like we have faced it before with the CUDA threads. Okay, so a very good package that allows us to interface the MPI library is what is called MPI for Pi. So the name tells what it's doing, and these are mostly wrappers. And the way to install it is like this, yeah. But anyway, this I have installed on the Python that we used before. And here we can import from this MPI for Pi module the MPI Python interface. Okay, and important concepts that we need to understand in order to be able to use the MPI is that when we will run our executable or your Python script, you need to provide how many processes you like to have. Okay, and when you have process, you can group them in different communicators. Okay, so if you have 4 processes, for example, if all of them, so when you try to execute your executable with 4 processes, and then the communicator that it creates that has all those processes, it's called the word communicator because it has all of them. Of course, you can create groups of those communicators, but usually you use the word communicator, and this will give us access to that word communicator. And through the code, you may get the size of the communicator. For instance, when from outside of your application, you give the number of processes, you can get it also in size. So you say, my communicator get me your size, and it returns you your size. And I just mentioned that each of your process gets a rank or an ID, like we did from the thread ID. Okay, and this function returns a different rank for different process. Okay, now I think we can go to see the examples that I prepared. This is in the last folder I have here. I think this was just a simple test. Okay, yeah, this is just a simple test to see this how this MPI works. I just put that I have the word communicator, I get the sign and the rank, and I print it. Okay, so in order to be able to use now this distributed computer, we will need the module load of MPI. So I have it here in the compiler. You need this module in order to have access to the MPI library. Okay, so don't forget to load that one. So if you load that one, you should have the MPI run. If you do which MPI run, you should be able to see it. Okay, and now we are saying MPI run minus n is the number of process. Let's say 1, Python, and then let's run the script. Okay, some warnings that are not so important, but you can see, ignore this warning. You can see it says that the communicator size is 1, and I am rank 0 that I'm printing. So if we can increase that to 4, you can see that they have printed 4 now processing the communicator, and they start printing, and of course are not in order because these we cannot control. Okay, so this again are the same concepts about parallel computing. Now, the example that I prepared, we have 2 vectors that we want to add. So how we do that? We let's say we have now a node that has 4 GPUs. So I hope that now when you did this alloc, or you may exit and allocate again, is to choose to have 4 tasks, and this grace option put GPUs to be 4. So to use all the 4 GPUs that the Cyclone node can provide to make things more interesting. Now we have this, let's say that this is our vector, this is our full vector. Okay, we want each GPU to be able to handle 1/4 of this vector. So the GPU 0 takes the first chunk, the GPU 1 the second one, okay, etc. And now one needs to think about the following issue. How I assign my MPI process to GPUs? This is one very good question. And the simplest one is that you will have one MPI process to speak to one GPU. For example, if you have 4 GPUs here, you will have 4 MPI tasks. And if you want to use more tasks, of course, you need to go to more nodes. For example, 8 GPUs, you need 2 nodes on a cycle. Okay, let's go to see the example. So let's go step by step to understand how this works. So I get my communicator, which is the MPI work communicator, get the size, the rank. And now with this import PyCUDA and auto init, it initialize the PyCUDA, and we are able to count how many GPUs we have on the node. Okay, and because we said that we want to bind one MPI process to one GPU, we want to check that the size of the communicator, the MPI communicator, it's equal to the number of the GPUs. If it is not, we can throw an error and exit. Now, this step here makes sure that the rank 0 GPU get access to the device 0, the rank 1 get access to device 1, etc. Okay, so this actually binds the process, the MPI process, to talk to a different device. And then this is, you create a context in the sense that you need to speak to a device and give it orders. This is what it does, and now it starts the calculation. Let's say that we make these big vectors that we did before, about 100 million elements, and we make it to, depending on the rank, to have a different seed. So we have different pieces of this vector per MPI process, okay, because this is a rank dependent seed. And then we create the 4 pieces that compose our vector. Yeah, the 2 input vectors A and B, and then C is the output. By the way, this n that we have here, it's for each process. So the total vector will have a size 4 times n, because we have 4 processes, for example. And now we do the what we have learned before. I mean, this is the lower level approach. We allocate memory on the GPU, and for example, you can check how much memory you use. This provides access to the function get information about my memory, and it can tell you how much memory you have free on the GPU and what is the total. Okay, just in case you want to check how much memory you utilize. And we make our source code as the module we discussed before in string, and yeah, this is the add vectors. So each process will go through this code and does a different thing per process, because this vector here that I have created are different. And of course, later you can copy the data back from the device to host. This is what I do here. And yeah, I get rid of this, my context, and then I'm done. You can check that if you do this using NumPy, you can get that the difference is 0, which means that it's correct and the same. And here one made us and gather, but of course, yeah, then gather will need to collect from all the process the amount of elements that they have. But yeah, for this size, it will give you out of memory issue, so I just comment it out for now. Okay, now let's try to run it. So in order to be able to run with 4 processes, as I said, do the salloc, ask for 4 tasks. These option tasks are the MPI tasks and 4 GPUs. Okay, and let's try to run it. MPI run minus 4 we said, and Python, this is a Python script, and let's execute it. Okay, so let's concentrate on the important parts. So those, we said that to check how much memory is used from each process, from each rank. So it prints here how much it has used, and then how much time each process wanted in order to add the vectors, and then it checks the difference. So as you can see, you have all the process doing this calculation, and then you can do also other things like gathering the data or doing more process. But always keep in mind that this piece of code will be executed in parallel for all the processes. So this was the interactive way, let's say, to execute this this script. There is also the non-interactive approach, that is it's something that you write a small submission script. I don't know if you are familiar about it, and you submit it, and this goes to the queue. So this is the non-interactive approach. So I have prepared here a Slem script for those who want to have a try. So it provides all the information here instead of putting them directly here on the command line in an interactive manner. Here is non-interactive. The account that we put before, the task, the reservation, that is EuroCC, and 4 GPUs. You can specify the wall limit of the job, and then you run here your executable with 4 MPI processes. Okay, so do we have questions up to now? Because this is very important to understand how distributed computing works.
Kyriako, I have a question.
Ne, Andrea.
Is it better to do this, to do the MPI communication on the device level instead of on the CPU level? Because if, for example, we had 4 nodes with 4 GPUs per node,
yes,
I guess we could do the MPI between the nodes and have each node communicate with its GPUs.
Wait a minute. So the GPUs, in order to be able to communicate with other GPUs, okay, you need special kind of features. You cannot do it directly without passing through the CPUs.
Yes, exactly. So they pass through the CPUs, and then
they pass through the CPUs, exactly.
And then we can use MPI between the CPUs, right? Instead of the MPI from the GPUs.
Wait a minute. I mean, the MPI specifies the process and how the MPI process which are running on the CPU work. Now the CPU communicates with the GPU that we have byte it to it, right?
Yes.
So there is this intermediate step to communicate the GPU to other GPUs.
Oh, okay. So just my thought was that could we do the same work without using the MPI version for? So it's not two different things. It's not when you do the MPI, you do the same thing if you use GPUs or even if you don't use the GPUs.
So let's take the following example. Let's say that we have two nodes, not one.
Yes.
Okay, how you will communicate information between the different nodes? Yeah, this is the question. You cannot. Okay, you need to be able to have a message passing interface. However, in the special case that you have one node, you can bypass this. But if you have a code that can support MPI, you can scale it to more number of nodes.
Okay, so
yes,
it always goes through the CPU. I mean, that is the key. It always goes through the CPU.
So there is a way that GPUs on different nodes can communicate through the network card directly. Avoid it goes through the CPU memory, and it's called GPU direct. Okay, most of the new cluster now support this. They have the network cards being CUDA enable in order to be able to provide the GPU buffers and copy the data so it avoids some overhead. Okay, but you still need to have an MPI GPU, an MPI CUDA aware implementation.
Okay, okay.
Okay, but I made this example so if someone was to scale this to more than 4 GPUs, you can do it. If you, for instance, don't want to use MPI, you are restricted in one GPU node. You can, of course, use multi-threading inside, and for instance, you have more than one core within one node and bind that core to a different GPU. You can still do it. It's just that MPI release your hands if you want to scale it up to more nodes.
Okay, okay, thank you.
Okay, more questions?
Kyriago, is it possible to combine what you are offering in terms of clusters with big data, for example, with NoSQL databases like HBase Hive? Is there infrastructure for that?
So the MPI, okay, allows you to access data in parallel. Now, the way that you structure your database, it's on you. So SQL is one approach. Now one needs to check if the kind of format that it stores the data is directly accessible to an MPI reader. This I don't know, because in our case, we don't use SQL. We just write it in our formats for databases. But let's say you have an SQL that can write it for
databases. Sorry, I missed that.
Our format of databases. We do not depend on any SQL format to read the data. So you can read your data in a binary format, whatever you like. Okay, and you can say that if it's binary, let's say that you have a vector and you write it in binary, and you write in double precision numbers, and then you have two MPI processes. Then you can point to the same file on disk, and you can give a different offset based on the rank. And different ranks will read and different chunk of data in this binary format. So you don't care about the higher level format. If you are able to store in binary in some order, you can read it from MPI.
Okay, so this is actually quite clear. So next question is that, for example, you would have a system like, is it possible to have or to request maybe a platform that has, for example, Hive that basically creates directly a map reduce problem that can actually use a number of nodes in a cluster?
I didn't understand the question. So if
so today it's basically low level, GPU programming, OpenMPI.
Yes.
I get that. If, for example, I want to harness the computational power of your cluster, okay, either using
of your class
of your cluster.
Yes.
All right. And is it possible to request or to have, for example, on your CentOS installed some packages, for example, Hive, and then I would have my data. So data is data. Yeah. So
what packages like Hadoop? What do you want?
Yes, you can have Hadoop, for example. Yeah. Also, on top of Hadoop, you would have Hive.
Yes.
And you can run your simple SQL, which is translated into a map reduce problem. And
yes.
Yes. So how is this? Is this request a little bit complicated? Or?
Well, I do not use Hadoop on Cyclone, but of course you can ask the administrators. I think it's okay if you use it, and you just need to specify a list of process.
Okay.
Okay, a list of nodes that you want to use, how many processes you want to create, and Hadoop can handle it behind the scene. Of course, it does not use MPI, Hadoop. It's using its own implementation in order to have fault tolerance, but it should still be able to work.
All right.
Okay, I haven't used it, but I know that you can use it, yes.
My last question is that for testing purposes, do we still keep our accounts, or our accounts is just for the training session?
Your accounts, I think, are for the training session. I think Stages can tell us for sure. But in any case, you can have a preparatory access, which is very simple to get.
Okay.
Okay, and you have some time to do the test that you need. It's very simple. You briefly describe what you want to do, and in a day you have your account.
Thank you, Giriak.
Okay, do we have more questions? Okay, so yeah, I think now I'm reaching the end. I discuss all of this. So yeah, finally we reached to an end. So let me summarize what we discussed today. So we discussed firstly how we can use medium level language like C++, and the ideas of CUDA kernels, the keywords global, device, the random time variables, the special syntax of providing arguments, all the API functionality, how we can do communication using shared memory. We can synchronize the threads, as we said. We can synchronize the host to the device, and we can do more funny things like overlapping communication with execution. We can use zero copy approaches. And of course, there are much more things that I haven't discussed. The list is endless, let's say. There are texture objects, there are bug conflicts, coastal memory, and many more features that one can discuss about GPUs. And then we have seen also how to use Python to implement code, PyCUDA, how we can compile inside a Python a kernel, and how we can use Cumblas. And we have seen examples like the fractal picture with JIT compilers, both for CUDA and for CPUs. And then we discuss the MPI and how we can have in a distributed way many GPUs. And this brings me to an end. I don't know if I have anything important to say, just a few things that there are also useful tools that one may want to use when it does CUDA programming. So CUDA provides its own debugger that helps you to find, for instance, memory access violation. It puts several assertions and it helps you with debugging. And we have also the NVIDIA Visual Profiler that allows you to profile your application, so it can do timings for you. It can give you hints how to improve the performance, how you can use more efficiently in different features. This, I think, brings me to the end of my of the session today. So do we have questions? Or we close?
No, Kyriakos, thank you.
Thank you for your time. Stajan, do you have to say? Do you want to say something?
Yes, thank you. First of all, thank you, Kyriakos, for your notes and your time and your explanations to the participants. For everyone, all of the recordings that have so far taken place, so except this one, are online now. Kyriakos, if you can send me your presentation, then I'll put that online as well. So you can access the videos through the website of the event. I have put on chat and on Slack a link to the feedback form for today's Kyriakos' sessions. Please take a couple of minutes to fill it in, because it doesn't take that long, longer than that. Thank you for participating. Thank you, Kyriakos, again. And tomorrow we begin at 10 o'clock on machine learning aspects by Nikos, and Christos will be your speakers tomorrow. And we are done for today. Again, thank you everyone for joining, and thank you, Kyriakos.
Thank you all. Yeah, thank you.
And
have a good afternoon.
If you have any questions, then you can ask Kyriakos for any follow-up.
Yeah, you have my email.
Yeah. So let's close for today, and we'll talk again tomorrow. Thank you all for your time, and thank you, Kyriakos, again.
Okay.
Bye, everyone.
Bye.
Bye.